In this video, we're going to talk about probability distribution function for a discrete random variable. Wow, that is a mouthful. So let's kind of pick out some of the words we do know from this title. We should know the word probability. And then we've talked about how the word distribution refers to a table. So it's no surprise that I kind of see down here in this example that we have a table with probabilities. And then the other word we should probably know is discrete. Discrete means something that is finite or countable. So it's this word random variable is kind of different. Okay. So a random variable describes the outcomes of a statistical experiment in words. So what we're talking about is we're running experiments and we often use the letter X to represent the random variable. So for instance, we'll kind of jump to this example just since it's here on the screen and we can see it. A child psychologist is interested in the number of times a newborn's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X equal the number of times per week a newborn baby's crying wakes its mother after midnight. So um, that's our random variable, the thing we're studying. And X would take on different values in this problem. So maybe X is 0. We kind of see that, meaning that the baby doesn't wake the mother up 0 times that week after midnight. Um, okay, so that's what a random variable is. And the discrete part is the fact that it's going to take on whole number values and a finite number of values. So a discrete probability distribution function, back up to the second definition now, has two important characteristics. Every probability is between 1 and 0, and the sum of the probabilities is 1. So the first makes sense. I mean, probabilities are between 0 and 1 anyways, meaning it could be 0 or 1, but that means that every other value is either 0 or 1. Um, and then the sum of all the probabilities is 1, meaning it's going to account for every possibility and they'll total up to 1, kind of like what we saw with sample spaces where it's all the possibilities. Okay, so let's look at this example here. Child psychologist recording this data. So just so we kind of understand what this all means and we kind of understand what this table is representing, these are the number of times the baby woke up the mom. Now, technically that it's after midnight. So meaning like they're assuming then that maybe the mother is asleep too and they're waking the mom up at that point. Um, so it's something specific about it being kind of in the middle of the night, quote unquote. So for this problem, X is taking on 6 different values. It could be 0, 1, 2, 3, 4, or 5. Nobody answered more than 5. So 5 was the maximum, meaning that the newborn does sleep some nights without waking up after midnight, but 5 nights out of those a week, maybe the baby woke up. Maybe the baby just had a really rough night. Okay. Woke up 5 times. But there you go. That's kind of what the discrete random variable is for this problem. Now, the probability in this problem is coming from data. So technically, all of these are also, we used the phrase previously, we called this relative frequency because we're looking at the percentage of each. And even though they wrote it as a fraction, it is a percent. It could be thought of as a percent if we wanted to go ahead and divide them. Now, this does represent a probability distribution function. So this is a discrete, and they use PDF often to represent probability distribution function, okay? Because number one, all of the probabilities are between 0 and 1. And number two, if we added all of these up, the 2 plus 11 plus 23 plus 9 plus 4 plus 1, that totals up to 50 out of 50, which is 1. So the sum of the probabilities is 1. And I'll write that using summation notation. So the sum of the probabilities, P of X, equals 1. Okay, so let's kind of look at this in a different example where we'll maybe kind of put it all together here. So suppose Nancy has has classes 3 days a week. She attends classes 3 days a week, 80% of the time, 2 days, 15% of the time, and 1 day, 4% of the time, and no days, 1% of the time. So suppose 1 week is chosen at random. So she goes through her term, she attends these percentage breakdowns, okay? So our random variable, they're kind of guiding us into filling this out. The number of days Nancy attends class per week. All right. So what values would X take on? Well, they actually kind of listed it for us. 3 days, 2 days, 1 day, and no days. So I'm going to put it in reverse order. So 0, 1, 2, or 3. So no other options really were listed. Okay, so now they want us to create the probability distribution table. So we're going to create a table kind of like the previous example. So we're going to have X values, which will be these 4 X values we just listed, and then their relative probabilities, which they gave us. So for 0, here, let me scroll up a little. That was 1% of the time. So here I'm going to go ahead and write 0.01. For 2, for 1, that was 1 day is 4% of the time. For 2, 15%. And 3, that's 80%. So let's make sure that that does total up to 1. So 5, 20, yep, that does. That totals up to 1. So good, we got all the possibilities. So there's our probability distribution function. Table. And then they ask a follow-up question. What is the probability that Nancy will attend at least one class? So at least one means that she will attend one class or possibly 2 classes or possibly 3 classes. So all 3 of those would work for this. So we would be finding the probability of 1 class plus 2 classes plus 3 classes, which would mean we'd be finding 0.04 plus 0.15 plus 0.80, and that comes out to 0.99. So 99% chance that she's going to attend at least one class, and it makes sense. That's also, we could think of that as the complement of the one case that wasn't considered, which was 0, that she attended no classes. There's only 1% chance that's going to happen. So it makes sense that it comes out to 99%.